Thank you all for sticking around this morning. I want to thank Lacey and David for the invitation to participate in the symposium, and my debate partner, Katie, who just gave an excellent presentation, and my colleagues in NYC. We've had various discussions about the application of species delimitation methods for a range of purposes. So I'm going to focus on three issues. They're going to be resolution, bias, and uncertainty, and how species delimitation, specifically through the multi-species coalescent, can help better resolve these specific issues. Now, the idea that you can use more liberal or more conservative estimates of species for any type of analysis is not a new idea. People have been thinking about this for a long time, and there's obviously different opinions. We haven't really made any resolution, but these ideas are out there in the literature. Now, this is a more simplified pipeline than David showed, but I think all the parts are in there. And what I want to show in here is that, so this is, I would say, a comparative biology pipeline. If you believe the current species, these good species, working well. Sorry about that. I'll stand here. Yeah. So it's working well. So we have our taxonomy. Work out the groups. We studied the speciation biology, get a really good understanding of how these groups have become reproductively isolated. Obviously, there's going to be some feedback here. There can be taxonomy can be updated, but the end point is really what we're interested in here. Is now we have our good species, and you can do them for any type of comparative analysis. You're doing diversification rates, looking at traits are involved, and this is really the pipeline that your hope exists if you really believe in this idea of good species. From my perspective, the field of phylogeography has really blown this type of pipeline up. I'm going to go through numerous examples of why this is the case. And it showed that there's problems at all these levels, and that we can really modify these things by looking at species through a phylogeographic framework. Now first, this idea of good species, they're often based on really well-studied groups. The concepts are, when we think about them, or there's a really heavy body of research, really understanding how these groups originate, whether it's Darwin's finches or African cichlids. And that kind of idea is kind of extrapolated across many other species which we have very little data. There's been really no analysis on them, but we're using those same units in the same type of analyses. And for example, reproductive isolation is often assumed, but not directly tested. Now the problems with taxonomy are well known. There's numerous papers out there that have shown the different types of issues arise, going back to this old Olin paper. But really what stands out to me is when I start to think about species spatially. So this is a geographic distribution of a really widely distributed North American songbird. That's a huge distribution. So that's considered one single biological species. And I think by lumping that together, you're losing so much information about all different aspects of the species biology. Now, for example, you might be comparing that to another group, another species that might have a really narrow range, and you're just losing a lot of information there. And here's some implications of spatial implications for a data set that we're wrapping up right now, where we're looking at an entire family of birds known as the gnatcatchers and gnat-wrens. So what we've applied the popular Dec plus J model to model range evolution on this phylogeny. So this is not a very species-rich group of birds, about 15 species in it. But really what we're interested in spatial history of this group, and you can also look at trait evolution. So there's one species here that's a long-distance migrant. So this would be their species tree based on biological species. And if you applied something, we applied BPP to a really dense taxonomic and spatial sampling, we get a very different phylogeny. So we've sampled over 95% of the described diversity, so there's about a threefold increase in the terminal units. Now, we can spend a lot of time debating about species concepts and whether things are structure or species, But to me, that gets really murky really quickly. And all the problems that you can think of taxonomy are in this tree. And birds are some of the most heavily studied taxonomic groups out there. So we have cases of paraphyletic species. We have cases of triptych diversity. And we have cases of undescribed lineages. For example, when we look at it from the multi-species coalescence, trying to model range evolution, it's much more clearer. We have a much clearer understanding of where the clade originated and how it evolved across the landscape. With respect to the origin of migratory behavior, as I discussed before, there's a single migratory species. When we apply BPP to that, we see that there's 7 recognized lineages in them. 4 of them are non-migratory, 2 are partial migrants, and 1 is a long-distance migrant. So this traditional taxonomic body, this is a North American, the Arctic bird. This information was not captured prior to doing this type of analysis, and it brings out much finer scale spatial resolution. Another way to look at spatial resolution is if you map a species tree on the landscape where we have, it's another genus of birds, but we have 2 alternative species trees based on just currently accepted diversity and the total diversity in the group. You can see there's a lot greater spatial resolution in there. And so if you're willing to accept that the multi-species coalescent is just giving you the population structure in there, and that if this is really what you want, you're losing a lot of information over here. And from my perspective, this is what I want to know. The other aspect of this is temporal implications. And so Kelly brought this up earlier in her talk. And I think this is something that's often underappreciated. Species concepts that we apply are atemporal. We're thinking about where species are right now, how they're interacting right now with each other. We know that these contemporary distributions may be very ephemeral. Well, there's no controversy in that ranges contract, they expand, the landscape is very dynamic. And the way to best incorporate this in understanding species limits is through the multi-species coalescence, at least in my framework. I don't know another way to do that. Other considerations. There's considerable bias in how lineages are delimited traditionally, and I think it probably exists today. We have really colorful groups that are attractive to humans that get split up like crazy, and then you've got groups with much more conservative phenotypes that are typically overlooked. And the extent of these biases, we don't really know. We don't have the data. We know they're there, but how widespread they are across the tree of life, we can only guess at this point. But I think it's safe to assume there are cases where this really can create big problems. Now I want to show you a couple examples of how we applied the multi-species coalescent to look at different systems. So we applied the multi-species coalescent to look at the origins of rainforest diversity, so we can get more nuanced patterns that aren't captured using traditional taxonomic approaches, and we can understand the distribution of diversity between different ecological assemblages in the Amazon basin. Another aspect where we use the multi-species coalescent, which Katie spoke about, is trying to understand the connection between micro and macroevolutionary patterns. And so we looked at the spatial distribution of shallow diversification rates and the connection between shallow diversification with higher phylogenetic rates of diversification. The only way we can do this type of study is by having standardized comparable units. We did that through using the multi-species coalescent. On the other end of the things, when I see these types of studies, it's not a criticism of this. It's a really nice study, or really robust job of resolving the phylogenetic relationships in a group of birds known as the tanagers. When they're doing a diversification rate analysis, and they see these really atypical spikes in diversification rates relative to other groups of birds in the family. And the question that I have when I see these types of analyses, are these rates robust to taxonomy? And the answer is we don't know. We don't have the data. Maybe for these particular groups, such as Darwin's finches, these good species that have really extensive empirical data sets, we have a really good understanding of them. But there's lots of other tips in that comparable work hasn't been done yet. So we can't really answer those types of questions yet. And finally, in comparative analysis, we account for uncertainty. If you open up any issue of systematic biology and you look across the program for this conference, a considerable amount of work is dedicated to accounting for uncertainty in comparative analyses, whether it's for topology, clade ages, trait variation, all this energy and making considerable progress in these areas. But one aspect we completely ignore. We do not include any aspect of uncertainty and species limits in these types of analyses. So to wrap this up, I would argue that if you want better spatial resolution, less bias, and less uncertainty in your analyses, your comparative analyses, whatever they may be, from my perspective, the best way forward is through the multi-species coalescence. Thank you.
All right. Questions for either of our speakers? Yes, I'll be there in just a second.